we continue. If not, we'll take up the problem we were considering in the last class, and that has to do with the flow of a fluid past a sphere. So we have sphere, center of the sphere as the origin. This is taken as the z-axis, and we have fluid flowing around. Flowing like this. So fluid enters here and goes around the sphere. So standard to consider the two kinds of forces what we consider, and where the two components V R and V theta are dependent on the variables R and theta. So the stream function definition to satisfy the continuity equation is given like this. And then we gave without proof that the stream function satisfies the following equation for steady and creeping flow. That's what we are considering. So the E square is given to be D squared by dr squared plus sin theta by r squared d by d theta of 1 over sin theta d by d theta. So we are asked to assume that psi is given by some function of r alone times sin squared theta. When you substitute it first into e squared psi, because e power 4 psi, nothing but e squared acting on e squared psi. So we given the formula for e squared directly. And so if I do that, now e squared psi we show is actually equal to e squared by dr squared minus 2 by r squared times f of r times sin squared theta. So I pointed out that e squared gives for us any function of r times sin squared theta gives the action of this operator which is dependent on r alone, right? So we can then argue that e power 4 psi is given by d squared by dr squared 2 by r squared acting on d squared f by dr squared minus 2f by r squared sin squared theta. It's just multiplying the whole equation. So this the e power 4 psi is going to be equated to 0. I'll get the differential equation in n, which I sort of roughly derived. The final answer is what I am going to write down. You can easily show that f will satisfy the following equation. This is what Birch will call as an equidimensional equation. So if you have r power 4 that multiplies fourth order derivative, r squared multiplies the second order derivative, and so on. So the solution, standard way to approach the solution is to choose or look for a solution that is proportional to r power n, where n is to be determined. So if I were to substitute this, so obviously the same f prime of r would be c n times n minus 1 r power n minus 1. F double prime would be c n minus 1 times n minus 2 r power n minus 2 and so on. You now calculate the third and fourth order derivative. you take all that and substitute it into the equation, then you will get the following fourth order equation in n. So I'll leave that as an exercise for you to do. This is the fourth order algebraic equation in n. You clearly see that the easiest, you have to find all the four roots. It might not always be easy. You can easily see that n equal to 1 clearly satisfies the equation. Right? You can also easily verify that n equal to minus 1 also satisfies the equation. In the general case, you somehow find a way of solving that. So if I find two roots, then I can simply divide the fourth order polynomial by the quadratic polynomial, n squared minus 1, and then I will simply get the rest of the, so that would simply be n squared minus 6n plus 8 is what you would get if we were to divide this. And so I've now found all the four factors. So this really gives n is equal to 4 and 2. So the values of n are minus 1, 1, and 4. Right? So the solution itself then is written. I'm not going to all it because we've already done it once for a second order equation. So this is just so I can write f of r as c1r, that using n equal to 1 as the first term, and n equal to minus 1 term will also come in, and n equal to 2 and 4. Right? So plus c3 times r squared, r equal to 4, and so psi is simply f of r times sine squared theta. And now requires to determine these four constants which have come out of solving or integrating the fourth order differential equation. So what we have to do is first be able to write down the viscous fluid flowing past a solid cylinder. So two of the boundary conditions would be the no-slip boundary conditions, in the sense that that would give two, one condition each for VR and V theta, right? So clearly, boundary conditions in terms of the velocity, right, are given by VR of R. Let's say the radius of the sphere is R, capital R. Theta is equal to 0, right? And V theta of R theta is also equal to 0. You can note this boundary condition on the surface of the sphere. Velocity is 0. Here they are written in terms of the components, the r and theta direction, so both of them would be 0. Now, what the third, the other two boundary conditions are coming from the fact that the velocity, what is called the free stream velocity, is given as v infinity times Ez. Right? So that is the velocity far away from the sphere. So for that, I have to take limit v going to infinity of v is simply v infinity times Ez, right? Assume it's in the z direction. If I'm given that, right, then I have to find the components of VR and V theta according to this. So wait, I'm sorry, this is R going in. VR would be simply V infinity Ez dot ER, which we can easily find from the unit vectors that we have written down, and similarly the theta would be V infinity Ez dot E theta. So I think this would probably be V infinity times cos theta. You have to go back and look at the expressions for either ER in terms of EZ or EZ in terms of ER. ER and E theta in terms of EZ. Okay, so this would be V infinity cos theta. This turns out to be minus V infinity sin theta. So these are the free stream boundary conditions, two of them, and the no slip boundary conditions, two of them. So now we have to convert this into boundary conditions on psi, because the whole equation, right, or the is in terms of psi, and the function we have solutions, we have found this only in terms of psi, right? So we haven't found either. One way of doing it is express now B of R in terms of from psi, express B of R in terms of R and theta, and directly apply those boundary conditions, right? You can use these equations to express PR and B theta. They would have the four undetermined constants, and then apply those boundary conditions. That's one way of doing it. Another way is convert these to boundary conditions on psi. You do one of them, you do the later one. So make the BR of R theta equal to 0, and B theta of R theta equal to 0 is very easy to write. So BR is minus, let me write those boundary conditions here. So this one, in terms of psi, so psi is BR is given by 1. BR evaluated at capital R will be minus 1 over R squared sin theta is by d theta of sin of R theta equal to 0. That's the first boundary condition. So d theta would be 1 over R sin theta d psi by dr of R theta equal to 0. That's the second boundary condition. And then limit R going to infinity, right? Br as R goes to infinity, Br will be as R goes to infinity minus 1 over R squared sin theta d psi by d theta is actually equal to B infinity times cos theta. And then again limit R going to infinity, B theta, which is 1 over R sin theta, d psi by dr is equal to minus B infinity sin theta. Right? So maybe it is easier to apply this first. R going to infinity means we can cancel out some of the terms. It's also easier to differentiate psi with respect to theta rather than with respect to R. So let me choose the first of the boundary conditions. Here, not the first, I'm talking to the third of the boundary conditions. In some case, it would be usually easier to apply the R going to infinity boundary conditions. Although you can do it whichever order you want. So let's take this now. Right? So psi is all of this. Right? So psi is f of r times sin squared theta, where f of r is given like that. So minus 1 over r squared sin theta. So d psi by d theta is f of r and 2 sin theta cos theta. So then minus 1 over r squared sin theta is minus r squared sin theta. So which is actually sin theta will cancel with minus the f by r squared, right, cos theta. This is what it is. Now I have to take a limit as r goes to infinity, equate it to b infinity cos theta and see what happens. What are the constants I can determine, right? So this is limit r going to infinity. by r square would be C1 by r. Now I have to explicitly write it. Plus C2 by R2 plus C3 plus C4 R square is equal to P infinity. With the fact that the cos theta comes out is indicative of correctness of this procedure. So if I take r going to infinity, then clearly I can, at this stage I am not saying anything about C1 and C2, I have to take them to be non-zero, right? So this will become 0, and so if this has to be equal to B infinity cos theta, clearly C4 has to vanish. That I can say, because the r goes to infinity, otherwise it will blow up, right? And so if C4 vanishes or take it to be 0, then that problem would arise, right? So clearly from this I get, and further I want this to equal B infinity cos theta. So clearly this would imply that C4 is equal to 0 and C3 or minus 2C3 is equal to B infinity, or C3 is actually equal to minus B infinity by 2. You get 2 of the constants, and you can easily verify that if I apply the other condition, this sort of becomes an either or condition which we might not know to begin with, right? So what I am trying to point out is that if I apply this condition also, you can easily, I want to keep that as an exercise. I want you to apply that. It's slightly more difficult in the sense you have to differentiate f with respect to r and then take the limit as r going to infinity. You should get the same result. That's what I want you to check if you are in fact getting the same result. Okay, so I am not going to pursue that. So now let's take up the other. So we determine 2 of the conditions. So let's take up the other 2 conditions. So minus 1 over. So I can now write psi as simply C1. So I know that C4 is 0. So C1R plus C2 by R plus C3 R. Even though I determine C3, I will just write it as it is, sine square theta. C3 is known, so I have to only find C1 and C2 from these 2 conditions. So let's apply the first condition. Minus 1 over r squared sine theta times d psi by d theta, that is 2 sine theta cos theta, right, of C1. Now this is evaluated at capital R, so this will be C1R plus C2 by capital R plus C3 R square is equal to 0, right? It is equal to 0, which would mean that C1R plus C2 by R is equal to minus C3 R square, right? Minus C3, I have determined that's one equation for C1 and C2. You can see the pattern whenever you have these kinds of free motion and far away from the surface of the whatever body when we see in the sphere whatever, right? So then you see that application of r going to infinity would simplify the function. Then you apply the closed with boundary condition. Here, of course, I would need both of them because I need to determine C1 as well as C2. So if I now do that, so that would be 1 over r sine theta. Now I have to differentiate this with respect to r, right? D psi by dx evaluated at capital R. So if I do that, so this would be C1 differentiating with respect to r, minus c2 by r square evaluated at plus 2c3 times r, and that also has to be evaluated at the surface of the sphere. So that times sine square theta is also equal to 0. So from this I get the second equation, that c1 minus c2 by r square is equal to minus 2c3 r minus 2c3 r. So that would be 2b infinity times r square. I'm sorry, c3r. So it's only r. So I can also make this divide 2 by r so as to make it close to similar. So this is what I am getting, right? So right away I can simply add the two equations and get c1, right? So 2c1 would be 3b infinity r by 2, which implies that c1 is 3b infinity r by 4. So I have determined the third of the four constants. So from that, I can easily determine c2 from either of the equations. c2 by r square is b infinity. c2 by r square is b infinity r by 2 times minus c1, which is 3b infinity r by 4. So 1 by 2 minus, minus c. So that is 3. Right, so which means that c2, this is minus 1 by 4. Right, so c2 would be minus b infinity r cubed by 4. So these are the four constants that have been determined, right? So now I can write the psi itself as b infinity is common to all the constants, but can be written as b infinity times sine square theta times 3 by 4 r times small r minus 1 by 4 r cubed by r minus half r squared. So you have to verify that I have written it correctly. C3 as minus b infinity by 2. That's exactly what I have, right? C3. And then C1 corresponds to this, so it must be 3 by 4 r times b infinity. It is also matching, and so this is C2, which is minus 1 by 4 b infinity r cubed. So that's written like that. So now, once I determine psi, I have to now go back and get Br and B theta, right? Because that's what I want finally. So this now completes the solution of the problem. So we find an equation that psi must satisfy, right? And then all the boundary conditions are in terms of the physical variables. So we have to translate it to the boundary conditions on psi, and finally get psi, and then get back the velocity from these equations. And so the final equations can be written as Vr is b infinity cos theta and it can be written like this. you can easily verify by doing this differentiation again and getting the answer. So I don't need all this. So that I will let you complete and verify these answers. So now what is to be determined is the pressure distribution. So what I pointed out, one of the objectives of what is achieved by introducing the stream function is we seem to decouple the velocity calculation from the pressure calculation, which is what I have done actually. What the velocity becomes, because if you look at the equation of motion as such, right, velocity and pressure are coupled in the equation. So the stream function approach provides a way of decoupling in a somewhat indirect manner, right, so that we get the velocity profile independently of the pressure profile. And we go back to the, when we took the third of the equation of motion to get to all of this, we saw that we cancelled out because the pressure term, the body force term could be written as a gradient of some scalar function. So that term simply cancels out. So go back to that step in the procedure. So that is the basis of the decoupling, right? So we get this. So now we have to go back to the equation of motion and get the pressure. So we have the equation of motion in three directions, r, theta and phi, and you can easily verify that the phi component, if you were to write, would simply give dE by d phi is equal to 0. So there is no variation of the pressure in the phi direction, which is what we expect, because the velocity is a function of r and theta, and that's also, that's not surprising, that's also reflected in the pressure dependence, right? So two crucial equations are there, which is somewhat complicated. So I'm not going to go through the whole procedure, but I'll write down one of the two equations, let's say dE by d theta, one in the theta direction, and tell you what is involved. So if I write theta direction, we get 0, because the inertial terms are all 0, steady creeping flow. Inertial terms are 0, right? So 0 is equal to minus 1 over r dE by d theta. These are the only terms that would remain. Rho d theta plus the business term would be 1 over r square d by dr of r square dB theta by dr plus in contrast to the one-dimensional case, if we are considering that hardly one of the terms alone would come into play, here you can see that the resistance, especially in the spherical polar, you see that 3 of the terms will contribute to the distance term. All of these you can see you cannot really make 0 just like that. The d theta is a function of r and theta. So all these, and dr is also a function of r and theta. So all of those would have to be calculated. So we have the Vr and d theta. So what I found was that it's simply easy to write this as infinity cos theta phi 1 of r, some function, whatever is appearing here, and this is minus b infinity sin theta of phi 2 of r. Phi 1 of r is just this term in the brackets, phi 2, just for convenience. Right? So first thing, what we need is an equation for dP by d theta, which I can take that over to the other side. It has then to be integrated. So what is rho times b theta? So clearly here g is minus g e z, because the z axis is first, the positive z axis is upward, right? So it can be written like this. And so you can easily verify that this would mean this is b theta. So b theta will simply turn out to be g sin theta. that we know how to do it, just as we did for this case. You have to take the Ez dot E theta. So there's a minus p here, and then that would, so where Ez dot E theta must be minus sine theta. So minus p times minus sine theta would give me plus j sine theta. So then we have to get to doing all of this. So we have here, so I have to calculate each one of these terms. So for instance, I can write dPr by d theta. It's easy to write it in terms of phi 1 and phi 2 and then combine it. Otherwise you get lost in, I'm just giving you a question because I want you to do the same procedure for the r component and to complete the integration. So dPr by d theta is the first thing I have to calculate, is simply minus d infinity sine theta times phi 1 of r. Now I have to calculate dv theta sine theta, d by d theta, v theta sine theta. So let's calculate that. V theta sine theta is minus d infinity sine square theta times phi 2 of r. So d by d theta of that would be minus 2 d infinity sine theta cos theta phi 2 of r. These are easy to write out because they don't involve the derivatives with respect to r. That problem will come here. Now I have to divide this by sine theta, again differentiate with respect to theta. So d by d theta of 1 over sine theta, d by d theta of d theta sine theta would be divided by sine theta and then differentiate with respect to theta. That would be 2d infinity sine theta again. So I have to divide by sine theta, so this term will disappear. Derivative of cos theta is minus sine theta, that in combination with this minus would simply give me this. Those are easy to write down. Now the somewhat complicated term is this, right? So let's dv theta by dr is given by minus b infinity sine theta times phi 2 prime of r. The prime here denotes derivative with respect to r. So I have to take r squared of that. So that would be r squared of phi 2. Then I have to differentiate it with respect to r. Right? Would be d by, so this prime of this. Right? So for me, prime is derivative with respect to r. So when I do that, so this would be minus b infinity sine theta times r squared phi 2 double prime over r plus 2 times r phi 2 prime of r. So what I have to do is to calculate phi 2 prime of r and phi 2 double prime of r. And phi 2 is given by this. Right? So I have to differentiate it once and then again. And so when you put all these together, the final equation turns out to be quite straightforward. I mean, conceptually simplified, and you get dt by d theta is equal to rho g r sine theta. Any of the terms would cancel, plus 3 r squared. This is what we get. Right? So this is what you should get. I'm going to leave it for you again to do if you have the time and patience to do it. Right? You can do it and verify. Right? So that procedure is straightforward. It's just a bit tedious because of the somewhat complicated dependence of the velocity on r. So we have to evaluate so many of these terms and put them all together. You simplify. So I can now integrate this without any problem. B itself would be integral of sin theta is minus cos theta. So I will get minus rho dr cos theta. So everything is so again with plus 3 again minus, so minus 3 r square plus some function of r, right? We have already used f, but here have plus some function of r, I call it c of r. So to determine c of r, we need an expression for dp by dr, and that turns out to be, for that we have to go to the equation in the r direction and do the same procedure, right? Again, a very complicated and tedious procedure would lead to dp by dr is equal to minus rho g cos theta plus 3. Of course, I can combine that to do. I'm just writing it as it is in my note. Cos theta can be easily combined. And so dp by dr is given by this. This is also much simpler than what it might appear if you actually look at the equation of motion in the r direction. Right? So now what I have to do is to differentiate this and get another expression for dp by dr, and you will then find that c of r is actually turning out to be a constant. So dp by dr from this is minus rho d cos theta, right? And then minus 3 cos theta times minus 1 over r squared. The derivative is minus 2 by r cube, right? This is what I have, plus c prime of r. So if you compare these two, you will see that this will cancel with this, and this again is plus, the 2 will cancel, and so this cancels with this. So we will imply that c prime of r is equal to a constant, which I may simply call as some p naught, right? As some p naught. Huh? Yes, c prime is 0. Yeah, c of r